let me write down the RG equation. So today the first thing we'll do is to try to prove the solution. That we get the solution, so we'll try to prove that solution is correct. So let me begin by writing down the equation first. So because so I'm going to drop mu from today. Of course, you should keep in mind that everything depends on mu, but because there is no derivative with respect to mu ever, okay, we can just forget about the fact that it depends on mu. So this sum over I equal to 1 to n. All right. Acting on and then we gave the solution if and G bar is defined. We defined G bar yesterday. So G bar alpha, which is a function of lambda and gr, it satisfies the equation that d lambda of this is equal to beta alpha okay, that was the solution. That f is given, f at lambda ki is given in terms of f at ki, okay, with a new set of coupling constants, which is G bar, and the G bar is obtained by solving this equation. Okay, this is a differential equation for G bar, and this is the initial condition that at lambda is equal to 1, G bar is the same as G bar. So our goal is to show that this solves this. Okay? Beta tilde, yes, thank you. Okay, everything is tilde. Yeah. Beta tilde was beta minus that d alpha. No, G alpha. So to simplify things a bit, okay, just in terms of writing, what I'm going to do is to write this in terms of log of f. This same differential equation I'll write in terms of log of f. Then you don't have to write this multiplicative factor of f every time. Okay, so let's write this differential equation for in terms of log of f. So there the equation is dd lambda of log of f lambda ki. Is this here? I just divided by f both sides. Okay. So if I divide by f, then this side becomes lambda del del lambda of log f, right? Derivative divided by f. Here of course f just gets divided, so that's this. And then here you get beta tilde alpha del del gr of f divided by f, that's del del gr of log f. Okay, it's just a reference to our criteria. The same equation. Pardon?
In the LHS,
Oh, lambda. And the solution also I'll write in terms of log. So log f, so this is supposed to be the solution. Log f lambda ki g alpha r is equal to first this log f pi bar alpha r. Pardon? Acting on yes. This thing, yeah. This whole thing is acting on. Yeah. So this is of course a multiplicative factor. Beta tilde alpha gr and then del del g alpha is acting on this log of this.
Sir, will not be the partial derivative in the LHS dd lambda del lambda.
Well, here the point is dd lambda means there is no other lambda anywhere, right? So I can write partial derivative, but it should be understood this what this means, right? I can put lambda del del lambda. Okay, so the solution is this plus log of this, which is just gamma tilde, yes, thank you. Okay, all of these are gamma tilde. Okay, there will be no beta or gamma. I mean, everything will be tilde because the equation here this depends only on gamma tilde. Okay, so let me repeat again. So what we need to show is that this log of f given by this, so this determines what the lambda dependence of f is, right? This satisfies this equation provided the g bar that appears inside this, okay, here it appears in the argument of f, here it appears in the argument of gamma tilde, provided that g bar is given by solution to this equation. Okay, yesterday we discussed an application of this, right? We are assuming this what it means, right? Basically at high energy, okay, if the theory is asymptotically free, then for large lambda you have to evaluate g bar at large lambda, okay, that is small, and that's the utility of this formalism. Okay, but today we will just try to prove this first, okay, that will satisfy this. So what we are going to do is that in this expression for log of f, we will substitute the right hand side and check the right hand side and left hand side are equal. Okay. So this is going to be our RHS and this is going to be LHS. So let's substitute for log f this and see what we get. So right hand side will be lambda del del lambda plus we have to take the derivative with respect to lambda. Okay, in this expression, lambda appears only here. Okay, this is just lambda prime. So if you calculate del del lambda of this, all it means that you have to evaluate the whatever is inside at lambda. Is this clear? If you have a to b of some function, integral a to b fx dx, ddb of that function is just f of b. Right? That's what we are going to use. So lambda del del lambda will just be this evaluated at lambda, the integral divided at lambda. So plus lambda times 1 over lambda gamma tilde. Alright, there is sum over I. Okay. Sum over I gamma tilde Ri of G bar lambda G bar. Is this clear? Now we are going to do one more step. Let's write this. Okay, see lambda dependence here comes through here. Okay. So let's take the derivative inside. Okay, and use chain rule. Okay. So that gives you sum over alpha del del G bar gamma, sum over gamma del del G bar gamma of log f I G bar alpha is equal set G bar alpha lambda GR times lambda L lambda of G bar alpha G bar gamma
Lambda dg lambda of G bar equals to between the right side of the board.
Right side of the board.
Yeah, right top corner that relation T G bar alpha.
Oh yes, thank you. There is lambda here. Okay, the equation that G bar satisfies is lambda dg lambda. So this I now replace using that by beta tilde gamma let me write it as a vector G bar lambda. Okay, sometimes I will write it as a vector, sometimes I display the explicit component, but writing it as a vector means it depends on all the components. Is this okay? Now you see that this is almost what you want, but not quite. Oh, I should have written this next time. Plus sum over I gamma tilde R I G bar. So this is almost there, okay, but not quite. Why isn't it quite the same thing? Because you see here we have beta tilde alpha of GR, right? Beta tilde alpha of GR. Here you have beta tilde gamma of G bar. Okay? The argument here is G bar, okay, not G. And the derivative also respect to G bar. Okay. Similarly here we have gamma tilde Ri of GR. Here you have gamma tilde Ri of G bar. Okay. So this equation holds at lambda equal to 1. Suppose you now evaluate RHS at lambda equal to 1. At lambda equal to 1, G bar is the same as G or GR, right? So del G bar gamma, this becomes del G gamma R. This becomes GR. And this also becomes GR. Okay, because G bar is GR, and then indeed this story. So what we have seen is that the differential equation that this left hand side and right hand side are equal at lambda equal to 1. Okay, but not for general lambda. Is this clear? The left hand side and right hand side are equal at lambda equal to 1, okay? Because the expressions are the same. So from here you can proceed in two different ways. One is to try to use group property. Okay, that you go from lambda to lambda plus delta lambda. Suppose you evolve from lambda to lambda plus delta lambda. Okay. To first order, you know that this equation holds. So 1 to 1 plus delta lambda. Okay. Then you apply it again at 1 plus delta lambda. Okay. You redefine all your couplings at 1 plus delta lambda and then apply it again. And this is the way you build the whole solution. Okay. So that way you can give an intuitive proof. But we will try to give a more direct proof. Okay. We will not try to use any group property or any intuition. We will just directly want to show that what you have here is exactly the right hand side. Okay. So for this we need another result which have to, okay, let me write it here.
So the way two sides are appearing, it's like one, if we just scaling as 1 over lambda.
Yeah, so basically this is telling you how to go from 1 to 1 plus delta lambda, right? That when you go from 1 to 1 plus delta lambda, the change in f that you get from this solution actually satisfies the correct equation. Okay, so up to order, if lambda was 1 plus epsilon, then to order epsilon you have got the solution correctly. That's what this is saying, right? Because this equation holds at lambda equal to 1. Okay. Then you go from 1 plus epsilon to 1 plus 2 epsilon. Okay. But you have to then make sure that the same equation holds at 1 plus epsilon. Because that is the way you can prove it using group property. But as I said, we will not try to use any group property, we will try to give a direct proof. Okay. Which is to directly show that this whatever appears here is what appears on the right hand side. Okay. So the relationship that we need to use is the following: beta tilde gamma of GR For now, we'll assume this and go ahead. Later on, we'll see how to prove this. Okay? So let's assume that this relation is true and see how we can use this to manipulate this. Okay. So here we have beta tilde gamma. Let's look at this. Fortunately, I'm running out of space. So let's see. Beta tilde gamma del G bar gamma okay, that's what we have. Because this is beta tilde gamma del G bar gamma. For beta tilde gamma, beta tilde gamma of G bar, let me have to write that. Beta tilde gamma of G bar. Okay, that's because here the argument is G bar. Okay, so beta tilde gamma G bar del G bar gamma is what we have. Now I'm going to use this to replace it in on the right hand side. So this is beta tilde delta of GR del G bar gamma and GR del GR delta. Times del G bar gamma. Okay, this whole thing is acting on this f, log f. Is this clear? Well, other possibilities that I just erase this at top and try to write things more explicitly. So what I'm claiming is that the first term beta tilde gamma G bar lambda GR del G bar gamma of log f, Okay, I'll not write the arguments of log f, it's all of this. This is equal to, I use this relation to write this as beta tilde delta of gr del g bar gamma lambda gr del delta r del g bar gamma of log f. Okay, log f, the argument is all of this. The argument is given here. Whereas by chain rule, this derivative is a derivative of log f with respect to delta delta g delta r. Right? Because where does g delta r enter? In the expression for log f, you can see right? The dependence on g, okay, gr, is through g bar. Right? There is no other place where g is entering. Right? So this by chain rule then just delta delta g delta r of log f. Okay? So let me write it on top. Right hand side is given by beta del gr del g r of log f. The argument is the same. Pi and g bar alpha function of lambda and gr. Plus we have this. Plus sum over I gamma tilde ri
That was beta tilde delta on
beta tilde, yes, all of it. Pardon? Sum over delta, yeah. Repeated index, yeah, sum over delta. So all repeated indices are summed over. So here there is sum over delta as well as gamma. There is sum over gamma, there is sum over delta and gamma. Now you see that this object over here, this first line, is what we have here. Beta tilde alpha gr del del g alpha. Right? That alpha has become delta there, but that of course is a summed over index. Now the arguments are correct, right? We have converted. So the trick is that by using this relation, we have converted the argument of beta tilde from g bar to g. Okay, by using this substitution, and in that process, you automatically also get derivative with respect to g instead of derivative with respect to g bar.
So what about the gamma?
Pardon? Gamma is still there, so you have to manipulate this now, right? So we have shown that this term is equal to the form, equal to this term, right? Now you have to compare these two. Okay, I think there is. Pardon?
So, this expression ki, there will be lambda ki, right?
No, not lambda ki, because I just substituted from the left hand side to right hand side, right?
Okay.
So that is this. Sorry, this is actually not no lambda ki here, right?
this is what we are trying to this phi is equals to lower one is
Oh,
just because that solution will be
yeah, okay, yeah, I agree. Yeah, I know. So you have to substitute for the solution. Yeah, in fact that is necessary. If so, log f of this, right? So is log f of this minus this. This lambda ki. Right. Okay, this is here you have a lambda ki. Sorry, here you don't have a lambda ki. Here it says ki, right? Here you need lambda ki. So it's still not equal. Okay?
And also the argument is G bar.
Yes, exactly. So this you have to now manipulate. Okay? So it's still not equal. We have to rewrite this log f using the solution in terms of this. Or we can do the reverse. We have got this, so let's erase everything here. This one I can write as sum over delta. I can now either start manipulating the right hand side. Okay, maybe I just do my right hand side. So left hand side. So this was not the, well, I labeled this wrong. This is the left hand side, right? And this is the right hand side. So what we calculated is the left hand side. Okay? So let's keep it as this and start with the right hand side. Okay, now I have even less space, so let's see how far we can go. I equal to 1 to n. Now, del G alpha. Now, for this, I'll substitute the solution again. Okay? Because I have to check that this solution that I have given gives equal left hand side and right hand side. Okay? So I substitute the solution again. So del G alpha of this. So that's log f of Pi and let me write G bar lambda star. Minus plus sum I equal to 1 to n integral 1 to lambda This fine. Now you say these two terms are the same. Right? Sum over delta, that is beta till the delta gr, del delta, and the arguments here are the same. Right? Ki, this is g bar. So what you have to worry about are the gamma terms. Right? So this term we can now forget. Okay, so left hand side and right hand side, let's say that this term and this term exist anywhere. Okay? So you can now focus on the gamma terms. So what are the gamma terms? So we have sum over I equal to 1 to n gamma tilde Ri of Gr plus sum over alpha beta tilde alpha of Gr del G alpha will now go inside this. Okay, it acts here. So there is still sum. Let me just put this sum all the way outside. Now we have integral 1 to lambda d lambda prime over lambda prime okay. Now here I can use chain rule because gamma depends on G bar, right? Gamma depends on G through G bar. Okay, so del G alpha of this is that you have to first differentiate G bar gamma with respect to G alpha and then differentiate this with respect to G bar gamma. So this quantity I can write as del G bar gamma del G alpha r. There is no other gamma anywhere, right? Yeah. Del G bar gamma. Okay, this is G bar gamma, but let's be clear about the argument. It's lambda prime Gr. Okay? Lambda is nowhere now. Lambda is only in the as the upper limit. Okay, so this argument is lambda prime. Del G bar gamma of gamma tilde Ri G bar lambda prime Gr. Yeah, now we can again use this. Is it clear? Because you have got the combination beta tilde alpha Gr del G bar gamma del G alpha. So let's erase that again. Well, sum over alpha is gone because we are using beta tilde alpha del G out gamma del G. Sum over alpha will be gone. So what will be index and gamma, right? And then del
It will be inside the integration.
yeah. Yeah, it will be inside the integration. Thank you.
Lambda will be like
Yeah. Integral 1 to lambda d lambda prime by lambda prime. So what did we get? Beta tilde gamma
Lambda prime.
g bar lambda prime gr, right?
Yeah.
And then del g bar gamma of gamma tilde ri. Is this okay? Okay, so now I think I can just erase this.
This was some kind of Taylor series of gamma tilde.
Well, we are not doing really Taylor series, right? This is exact. We have not done any expansion. Okay? Now we are going to use the fact that this quantity is lambda prime, del lambda prime of g bar gamma lambda prime gr. Because g bar gamma satisfies this equation, right? G bar gamma lambda prime gr is beta tilde gamma of g bar. Remember the definition of G bar, right? Which I have erased, right? But that was the defining equation for G bar. So now you see that lambda prime cancels. This 1 over lambda prime, okay, and this lambda prime cancels. Okay, so this lambda prime is gone. This one and this one. What we have is del lambda prime of G bar gamma. Del g bar gamma of gamma tilde ri. But this is just the lambda prime derivative of gamma tilde ri by chain rule. Suppose you want to calculate lambda prime derivative of gamma tilde ri, right? Lambda prime dependence comes only through this g bar, right? So this is the lambda prime definition derivative. So this I can write. Let me write one more step. Sum I equal to 1 to n gamma tilde ri of gr plus integral 1 to lambda d lambda prime over lambda prime is gone d lambda prime of gamma tilde ri g bar lambda prime gr. Is this clear? Okay, now you're almost there. This is of course a total derivative, so you can integrate and express the difference between the values here and here. So this is sum I equal to 1 to n So what is this? G bar of 1 GR? GR. Right? By definition. Because under the initial condition. This is nothing but GR. Okay? So this then cancels this. Okay? And what you are left with? Sum I equal to 1 to n gamma tilde Ri G bar. Okay, and that is what we want. Okay, so this then shows that indeed the two sides are equal. Okay, that the solution that we wrote down actually satisfies the differential equation. Okay, this proof looks a little complicated because we didn't use a group property, right? And because we didn't use the group property, we actually had to, basically this required that we have to determine the derivative of, see, G bar is a solution to a differential equation, okay? And the GR enters the expression for G bar in terms of initial condition, right? Not as parameter of the differential equation. Okay? And what this analysis required is that we have to find a way to express the derivative of GR, the G bar, okay, as a function of the initial condition, right? We are trying to look for the sensitivity of G bar as a function of the initial condition, right? Because those are this equation basically encodes that.
This one will require the group property. This.
No, we will do it without group property. So we will not prove. So the only thing that remains is to prove this now, right? Because you have assumed this to be true and then we have shown how to prove this.
So why we are going in a reverse way, assuming the solution and putting in the equation and checking the.
Well, the point is that the solution, because in terms of lambda, it's a first order differential equation.
Yeah.
The solution is unique.
Okay, yeah.
Once the one initial condition is satisfied, right? So the solution that you have given satisfies the initial condition because at lambda equal to 1, it gives the right answer, right? So that we know that this is a solution. If you want to prove that this is a solution, right? That's the solution, right?
No, no. I am telling that from the beginning actually the means combining this RG flow equation and the variation of lambda equation.
Yes.
So we get a differential equation which is first order differential equation.
That's right.
So why not we are solving this but we are assuming that there
The point is that this first order differential equation involves also partial derivatives with respect to other variables, right? So that's why that it looks more complicated. It's not just an ordinary first order differential equation, right? We can think of this as a first order differential equation in the variable lambda, but it involves derivatives with respect to the other g's, right? That's why you have to go through somewhat of a roundabout way in the sense that we have to define this auxiliary object g bar, right? And we express the result in terms of g bar, right? It's not that the solution is expressed directly in terms of gr, right? Okay, and the reason for that is because it also involves partial derivatives with respect to gr, the equation. Okay. As I said, the other way to do is to use the group property, right? We showed that the differential equation holds at lambda equal to 1, right? So from 1 to 1 plus delta lambda, you can easily go, right? And then you start from 1 plus delta lambda, you redefine your coupling constants at 1 plus delta lambda, and then apply it again. Okay. So to do it that way, you have to prove that this equation has the group property, right? That if you go from lambda to lambda plus delta lambda, and then redefine lambda plus delta lambda as your new lambda, redefine that as your 1. Right? You define all the coupling constants at that value, and again apply the differential equation. That is the same differential equation that you have to satisfy. Right? So once you prove that the differential equation has group property, then you can also do that. Right? Then it's just enough to show that it satisfies the differential equation at lambda equal to 1, because then you can go from any lambda, okay, by renaming your variables and then apply it at lambda equal to 1. Okay, so this is more a brute force method, right? We just assume that you don't know anything, we just want to check if this satisfies the differential equation, right, without using any intuition from group property. But the reason that this is not, the solution is more complicated than normal ordinary differential equation is because it also involves derivatives with respect to the other variables. And it's just not just an ordinary differential equation one variable.
So here this validation of this equation doesn't require the group property.
Which?
This validation of the equation, whatever we have proved, is
Yeah.
solution of
So the proof that we gave, right, didn't explicitly use a group property, right? But the reason that it works is because the equation has group property, right? Which I didn't discuss. But on the proof that you gave, we didn't use group property anywhere, right?
That's why I was thinking that maybe in this condition probably is some, because it is the group property which helps us to.
Yeah, but the group property is the property of the equations. I'm using the equations, right? So it is true that you can check that the equations do have group property. Yeah, and that's why the solution is writable in this form. Okay, but we didn't explicitly use it. That's all. Is this clear? Okay, so we still have to now show how to prove this. So to prove this, let's define f alpha of lambda Okay, there's a difference between the left hand side and the right hand side. So our goal will be to show that f alpha vanishes. Okay, so proving this means to show that f alpha vanishes. So first let's calculate f alpha at lambda equal to 1. So what is the value of lambda equal to 1? It's beta tilde gamma gr. What is the value of this at lambda equal to 1? Basically delta alpha gamma, right? Because g bar is the same as g alpha, right? At lambda equal to 1, g bar alpha lambda gr is gr alpha. Okay, so this is delta alpha gamma, minus, what about this one? Beta tilde alpha of gr, right? Because g bar is gr. So this is obviously 0. Okay, this is 0 for all gr. Okay, let me write, maybe I should put the gr argument explicitly so there is no confusion. So this is true for all gr. So what we are going to do now is to derive a differential equation for this f alpha and then show that the unique solution to the differential equation is f alpha equal to 0 for all lambda. Okay, this will serve as the initial condition for the differential equation because you already know what f alpha is at lambda equal to 1, and that will be good enough for us. So let's try to derive the differential equation. So let's calculate so here the lambda dependence comes here. see here lambda and gr you are thinking of independent variable. Right? So we can take del del lambda inside through del del g gamma, right? These two compute. Okay? So I can write this as del del g gamma r times del del lambda of g bar alpha lambda gr. Maybe I put a lambda here, okay, so that so this is one term, and then we have minus lambda del del lambda of this. Minus lambda del del lambda of beta tilde alpha g bar lambda gr. Is this okay? Now we are going to use the fact that lambda del del lambda of g bar alpha, this quantity over here, is beta tilde alpha of g bar. So you can write this. The first term will be beta tilde gamma gr del del g gamma r of beta tilde alpha g bar minus here I use chain rule. Okay, del del lambda has to go inside the g bar, so I can write it minus this as del beta tilde alpha g bar but this is beta tilde gamma of g bar. Right? Okay, so the goal is that we want to bring an f on the right hand side. Okay, we have to manipulate this so that we get this combination. Okay, then we get a differential equation for f, right? That's the idea. So let's go as far as we can. So this is del del g gamma r of this. So beta tilde gamma of gr. Okay, I think once more we have to do chain rule and then it will be done. So this I can write as del del G bar delta beta tilde alpha and G bar lambda G bar times del G bar delta lambda G bar del G bar. The first term and minus the same as the right once more. Del beta tilde alpha G bar lambda G bar This is okay? Okay, basically the idea is that we start from here, okay, and then differentiate as many times as possible using chain rule. Okay, that's what we did. We applied lambda del del lambda, okay, replaced it by this, applied chain rule, and here we applied chain rule, okay, and then replaced this by beta. Because we just did it in the reverse order, right? In one case, we first used chain rule, then applied the equation for G bar. In the other case, we first applied the equation for G bar and then applied chain rule. So now, do we have an F? That's the question, right? We want to see if this is related to F.
Alpha del G bar
Comes out.
Okay, what comes out?
del beta tilde alpha by del G bar.
Okay. So del beta tilde alpha G bar lambda G r del G bar delta. I can always change the gamma to delta, right? This comes out. What is left is beta tilde gamma of GR and here is beta tilde delta. This is clear? I just took this part common, right? Del beta tilde alpha, del G bar delta, right? I can always change this gamma to delta, right? So that part came out, and then what is left is this. But this quantity should be F. It better be F. The F delta, right? Is this clear so far? Okay, so this then I can write as del beta tilde alpha G bar lambda G bar del G bar delta times F delta of lambda G bar. Okay. So let's write the equation again, the full equation. So what we then arrive at is this. Okay, F satisfies an equation of this form. So now let's say how to interpret this. Beta tilde as a function of its argument, of course, you calculate from perturbation theory, right? Because beta tilde is beta minus that d alpha g alpha. Okay, so beta tilde you calculate in perturbation theory. This object g bar as a function of lambda and gr, you calculate by solving the differential equation. Okay, d g bar lambda del del lambda of g bar is beta tilde of g bar. Okay. So this we have already done. These are all known functions of lambda. Okay, so this quantity that is appearing here is some known function of lambda and gr. So now you think of this equation as an equation for f, which tells us how f varies as a function of lambda in terms of some known function of lambda and gr. Okay, this is unknown. Okay, this is known. This is a first order differential equation in many variables, of course. Okay, because you have f alpha for different alphas, you have different f's, for different grs, you have different f's. Right? But nevertheless, it's in lambda, it's a first order differential equation in many variables. Okay, or not many variables. The differential equation, the derivative with respect to lambda. Okay, we can think of this as many component vector. It's as if it's a first order differential equation of a column vector, right? But the column vector is labeled by alpha as well as the various values of gr, right? The continuous variable gr. Okay. Nevertheless, in lambda, it's a first order differential equation. So if we specify its value at any particular value of lambda, that's enough to determine the solution to the differential equation. Is that clear? So it's like dd lambda of some vector is equal to something times a vector. Right? That's the structure that it has. Okay, whatever that something is, if the vector is given at some specific value of lambda, the solution is unique. Now we know that here we know what the vector is at some value of lambda, namely lambda equal to 1 gr is equal to 0. This we had already seen. Right? This is 0 for all alpha and all gr. So then what is the solution to this equation? With this initial condition and this, it has to satisfy this differential equation. Yeah, 0 is the solution, right? If you said f alpha equal to 0, it satisfies this and this. And you know the solution is unique. Right? So the only solution is f alpha equal to 0. Right? So this shows that f alpha lambda gr. Yes. So what I'm saying is that so f alpha is determined by the solution to this equation with this boundary condition. Okay. Now because it's first order in lambda, we know that the solution is unique because the boundary condition I have already given, so that is a unique solution. So if you can find out any solution which satisfies this boundary condition and this differential equation, then that is the correct solution. Right? And I'm saying that f alpha equal to 0 is obviously a solution to this equation. then it solves this and it solves this. This equation has other solutions, but those will have different boundary conditions. Right? If you started with f alpha at lambda equal to 1 to be some other vector, then of course the solution will be different. But because you know that the initial condition is this, the unique solution to this differential equation is f alpha equal to 0.
So we just have to show that it satisfies the first order difference.
Exactly.
Other two.
If it has a second order differential equation, then you have to specify not only f but also its derivative with respect to lambda at some initial value, and then if both of those vanish, then you can again show that the unique solution is f alpha equal to 0.
Probably this particular sentence will require this group thing, like we have to given the solution, we have to evolve only because this equation, differential equation is first order. Just one constant will fix it. Otherwise, suppose we have more derivatives, we will require more constants.
Yeah, the point it doesn't require group theory as such. You can this is a statement of a differential equation,
Yeah,
right?
exactly. But
You can formulate it in the group in terms of groups,
yeah,
but you don't have to.
So also,
It's just if you have a differential equation of many variables, right? But this is a property. Suppose you have here there are many variables because f alpha not only is a function of lambda of course, but it has many alphas, and for every gr there is an f alpha,
yeah.
right? So you can think of this as a function of many variables, but the general structure that you have is this that it's lambda dd lambda of fi, okay, where I stands for alpha as well as information about gr, is some aij ft. That's the general structure of the equation, right? Where aij is a complicated functions of the I and j, okay? Because that involves all this dependence on lambda, gr, etc. The claim is that this equation has a unique solution if you specify the whole vector fi at lambda equal to 1 or any value of lambda. Okay. And at lambda equal to 1, fi is 0. Right? So fi equal to 0 at lambda equal to 1. Okay, so this is enough to show that fi is 0 identity. Now, instead of saying that you are using group property, I mean, you can also say that the group property is used based on this equation, right? I mean, that's because it's just a differential equation, right? It's a property of a differential equation that we are using.
Yeah, exactly. But what goes behind proving that first order differential equation? If you just specify one boundary condition, that will uniquely that fixes the solution uniquely.
Yeah, but that you don't need group theory for that, right?
What
It's a property of a differential equation.
No, looking at the differential equation, we can say that first derivative at lambda equals to 1 vanishes.
Yes.
Okay. So
Not first derivative.
yes, because at lambda equals to
Yeah.
1,
F is 0, yeah.
okay. And now, if you take the first derivative is some function of lambda into f lambda.
Yes.
So if you take another derivative, it will be either f lambda plus del f del lambda. So again, all higher order derivative will
Yeah,
vanish.
that's
So function is uniquely 0 by
Exactly.
Taylor series
Yeah,
expansion.
that's right. So what if the function vanishes, right? And it satisfies the first order differential equation, then all its Taylor series expansion coefficients will vanish,
Yeah.
right? And hence it is 0. Right? That's another approach to this.
Except one ambiguity that if we take f lambda, I mean if you divide this equation by f lambda, it will pick a log f term.
That will give you a log bt in the right hand
Like
side.
Yeah.
del del lambda log f, if you divide this equation by f lambda,
Yes.
so and this is a function of lambda,
Exactly.
this quantity
Yes.
by lambda, that lambda will be there.
Yes.
You have to integrate it out. So it can have some structure that e to the power minus 1 by x square,
Yeah.
which is a special kind of function that all derivatives are 0.
That is true. But the point is, because this equation holds at all lambda, right? You can check that you cannot get any non-zero result. See, another way of saying this, I mean, you can get a solution to this as an exponential. Right? This equation has an exponential solution, right? You can diagonalize a and then write it as e to the minus. Suppose a is a diagonal s inverse. Then the solution up to rotation by s is exponential of this eigenvalues times t times lambda, okay, times log lambda times the initial value. Okay. And if the initial value is 0, then the multiplicative factor gives you 0. Is this okay? So this basically proves the result. Okay, it proves that the sub result that we used. Okay, and then based on the sub result, we have proved the earlier result, right? That the solution that we had written down does satisfy the correct RG equation. Okay, so then that is the correct solution. Take questions. Okay, so maybe in the last few minutes, okay, I'll just complete what I left of yesterday. See, if you remember, yesterday we were discussing gauge theory coupled to fermions. And we solved the RG equation to get an equation of the following form. The T bar square was where this AG was taken to be minus B. And that was the definition of B. So this is G bar of lambda. You remember this? This was the solution to the RG equation, right? We got. And then for large lambda, this was 1 over 2b log lambda. Now in the solution to the RG equation, we had this factor, exponential of okay, this was one of the factors in the exponent, the gamma r. Okay. So the full factor was gamma tilde ri. Right? There is a full factor was gamma tilde ri. Gamma tilde ri. This was what? D tilde ri plus gamma ri. Right? D tilde ri was the canonical dimension. Okay. So when you had sum over I, gamma tilde ri is the sum over I this plus sum over I gamma. Alright, so this sum over I d tilde ri is what we had called d yesterday plus sum over I gamma. So when you substitute, so when you calculate integral sum over I 1 to lambda d lambda prime over lambda prime, there is one piece which is sum over I 1 to lambda d lambda prime over lambda prime times d, the dimension. And then there are another piece sum over I integral 1 to lambda d lambda prime over lambda prime times gamma tilde gamma ri. So this part of course is trivial to evaluate, right? This is just d log lambda. Okay, and when you raise it to the exponent, it just becomes lambda to the d. So that part is the trivial scaling part. This is the non-trivial part. Okay. So to evaluate this, we'll use the fact that the gamma ri typically has the structure. It begins at ai g bar lambda bar lambda prime square. Okay, this ai coefficients again you can calculate from perturbation theory, right? How do we calculate the ai's, right? We calculate the z tilde i's, right? Or a, let me call it a. Okay, we calculate the corresponding z tildes, and using z tildes we can calculate the corresponding anomalous dimensions, right? That's what we defined the anomalous dimensions. So we calculated this in terms of the renormalization constant that appears in z tildes. Okay. So now if you substitute this, what we will get is sum over I integral 1 to lambda d lambda prime over lambda prime a ri, and then g bar lambda prime square. Okay, so for g bar lambda prime square I can use where did I go? Here 1 over 2b log lambda prime. Is clear? I used g bar. Okay, it's expression for large lambda. Okay, because we are looking at large lambda, so this becomes sum over I a ri 1 over 2b log integral d lambda prime over lambda prime log lambda 1 over log lambda prime, right? That's log lambda plus a constant.
So G bar you are replacing G R.
Pardon?
You are replacing G bar with.
I am replacing g bar by this, and I am taking the gr, the lambda goes large lambda limit, right? In which case it just becomes this. This is clear? See, by taking the large lambda limit, of course I am making some error near the lower end. Okay, that's why I have written this constant piece with it, right? But for large lambda, if you want to know the behavior for large lambda, right, the lambda dependence comes from large lambda prime, right? So that's why I am replacing this. Okay, but there is a constant addition because near lambda prime equal to 1, of course, this formula is not quite correct, right? So there will be a constant part that is being added to it. But the lambda dependence is given here. Is this point clear? Okay. So in the amplitude, this is in the exponent, right? Because in the expression for f, it was exponential of this which appeared, right? So let's see what it does to the exponent. So f of lambda ki gr was given by exponential, okay, let me write the whole expression, integral 1 to infinity sum over I gamma tilde I times f evaluated at ki and g bar. So there is one effect, which is that the effective coupling in the expression for f will be replaced by g bar. Okay, the momentum will be brought down to some finite value for large lambda, and then there is this exponential multiplicative factor.
So in the exponent there will now be the integration multiplication.
There will be no.
There is an integration in the exponent you have written this.
Oh, I have written twice. Yeah. So this integral, part of it is just d log lambda, right? So that's lambda to the d. So this gives you lambda to the d. Then there will be a piece which is exponential of this. Right? This is given by log lambda to the power sum over I ERI by 2b. And then this f. Okay, this will be the behavior for large lambda if you have an asymptotically free theory. Okay. So what is the interpretation? This is the standard scaling dimension. Okay, if there is no renormalization, okay, then at large lambda you just get lambda to the d, just for dimension analysis. Okay. This term is what is called the scaling violation. Okay, it doesn't quite scale as lambda. Okay, it scales as there is additional factor of log lambda to something. Okay. This factor is controlled by the anomalous dimension of the fields whose correlation function are trying to calculate. Okay, because these ARIs came from gammas, right? These are coming from the Liouville constants. Okay, so these are electric anomalous dimension. Okay. And then it says that you have to evaluate the original amplitude at fixed momentum, okay, not at large momentum, but with different coupling. Okay, in fact, this coupling we got the expression. It was like 1 over 2b log lambda. Yeah, so there is lambda dependence. So first of all, there is a lambda dependence coming from here. Okay, this is the overall scaling dimension. Then there is a scaling violation which is coming from here. Okay, which is because of the anomalous dimension of the fields. Okay. And finally, there is a lambda dependence that will come through G bar, right? Because in any given scattering process, okay, the leading contribution comes with some power of G bar. 5-4 theory, 4-4-5 scattering, right? The first non-trivial scattering occurs at order lambda, right? 2 5s coming, 2 5s go out, that occurs at order lambda, right? So in any given part of theory, the leading non-trivial contribution, by non-trivial I mean where there is no separate momentum conservation, okay, which is actually a connected diagram, has some powers of the coupling constant. Okay. So how many powers of the coupling constant there are will determine some another power of log lambda, because the coupling constant itself is going as 1 over log lambda. So besides, in an asymptotically free theory, besides the usual scaling dimension, which is the lambda to the d, what you will have is some factors, multiplicative factors of log lambda. Okay, part of which comes from the scaling violation, and part of it comes because the coupling itself depends on lambda. Okay, and the process may involve some parts of the coupling. So this is the general structure of an amplitude. Okay, that because this log lambda is a very slowly varying function, it would appear as if that the leading contribution for large lambda is following the canonical scaling. Okay, lambda to the t. But then if you do your experiment carefully, you will see that it's not exactly lambda to the t. Okay, there is some violation from scaling. Okay, and that's proportional to log lambda, some part of log lambda. Okay, so this is a general structure of high energy scattering amplitudes in QCD, for example. Okay, in the theory of strong interactions, which is asymptotically free.
So in this equation, suppose we take the lambda going to one limit.
Yes.
Then whatever divergence is coming from this log lambda, that should be exactly cancelled by
Well,
this one.
yeah, that's because of this constant, right? This log, I've written log lambda, right? Here lambda equal to 1 gives you 0. But the point is that this, in this equation, I substituted this as 1 over 2b log lambda prime, right? But this, of course, is not valid all the way to lambda prime equal to 1, right? So what one should really think of is that you do the integral from 1 to lambda naught, some fixed number,
Maybe E.
okay, which is some large and fixed number, and then from lambda naught to lambda, right? That 1 to lambda naught integral is just some constant, okay? And then you have the lambda naught to lambda prime, lambda integral, right? That will not have this feature, right? It will be like lambda over lambda naught. Okay, so that's a general structure. So this divergence at lambda equal to 1 is just, I mean, that's not physical, right? It's just because the way you have written the other calculation. This is really valid for large lambda. If you want to find the extra behavior of this correlation function for large lambda, then you can use this one. Is this clear? Okay. And how large a lambda you need to have this formula depends on how closely the gr square, we wrote down the asymptotic form, gr square equal to 1 over 2b log lambda, right? How closely that approximates the actual gr square determines how closely you will get to this formula. Okay, so I think I'll stop here and continue tomorrow.